Now that we are familiar with the various thermodynamic properties which are used to describe the state of moist air, we can proceed to typical psychrometric processes of importance in air conditioning. You know that a thermodynamic process requires a substance to undergo a change of state, and when we study psychrometric processes, that is equally applicable here. That means when a process occurs, the moist air undergoes a change of state. And the first process that we will start with is adiabatic mixing of two streams of moist air, which is schematically shown on your screen. And we have got two ducts carrying two moist air streams, which are then combined into a single stream, and the resultant state is shown by state 3. The process of mixing of the two air streams is adiabatic. That means the ducts are completely insulated or perfectly insulated, so there's no energy exchange with the surroundings. We can easily perform energy and mass balances for this particular process, and starting with the energy balance, the energy content of stream 1 plus the energy content of stream 2 will give us the energy content of stream 3, that is m dot a1 h1 plus m dot a2 h2 is equal to m dot a3 h3. M dot a, remember, is the mass flow rate of the dry air. The mass balance on the dry air is quite straightforward. You simply add the two mass flow rates and you will get the resultant mass flow rate at state 3. To apply the mass balance for the water vapor, remember that the humidity ratio is defined as the mass flow rate of water vapor per unit mass of dry air, and we can, for steady state systems, we can, instead of saying mass, we can say mass flow rate, that is mass flow rate of water vapor divided by the mass flow rate of dry air, which means that the mass flow rate or rate of water vapor is equal to the humidity ratio times the mass flow rate of dry air. And that simple expression, that m dot v is equal to m dot a into w, will be applied to streams 1 and 2 and the resultant stream at 3. That will give us the equation for the mass balance of water vapor for adiabatic mixing of two moist air streams. The same process can be shown on the psychrometric diagram, and we have marked states 1 and 2, and you will see that state 3 will always lie on the straight line connecting states 1 and 2. Where on this straight line you will have state 3, that will depend on the numerical values, but it will lie on this straight line. It could be closer to state 1, it could be closer to state 2, or it could be very well be in the center. That will depend on the numerical values that we are going to work with for a particular problem. And that is what we will do next. We will go through a example of this process in which we are given a certain volume flow rate of air at certain dry bulb temperature and wet bulb temperature, which is adiabatically mixed with another air stream at a different dry bulb temperature and relative humidity and a different volume flow rate. And you are asked to find out the dry bulb temperature and the wet bulb temperature of the resulting air stream. So when you work with problems of this nature, the first thing will be to identify what process you are working with. In this particular case, because we have only studied one process and we are doing a problem related to this, it's quite obvious. But when we have studied several processes and you get a problem, the first thing you should be able to do is to identify the process. Once you have identified that process, sketch it on a psychrometric diagram. I'm saying sketch it. Do not directly go to the psychrometric chart, but first sketch it. Make sure you label it properly, which state you are representing as a state 1, which is being represented as state 2. It's up to you, but it should be clearly identified on your sketch. Once you have done that, then you can go on to the psychrometric chart and find out the actual values. You will see, because we require the mass flow rate of dry air and you are given the volume flow rate, we will need the specific volumes at states 1 and 2 also, and we will also require enthalpies. And to do that, I will just go to the psychrometric chart. You can see that I've already marked out 2 points over here. One over here, which you can see has a dry bulb temperature of 4 degrees C and a wet bulb temperature of 2 degrees C. The wet bulb temperature, constant wet bulb temperature lines are these dotted lines over here, and I will again just to make it clear show you that it is actually 2 degrees C. This is 5. This one over here is going to be 4. This is 3, and this line over here corresponds to a wet bulb temperature of 2 degrees C, and this line over this is 4 degrees C, this is 2 degrees C, so that gives you the state of the moist air stream. That is 4 degrees C wet bulb temperature and 2 degrees C 4 degrees C dry bulb temperature and 2 degrees C wet bulb temperature. The other air stream has a dry bulb temperature of 25 degrees C and it is having a relative humidity of 50%. So this is 25 over here. We go straight up where this line intersects the 50% relative humidity lines, that is state 2. So if I just want to show it over here, this will be state 1 over here, and we have state 2 over here. And state 3 will lie on a straight line connecting states 1 and 2. As I said earlier, we will need the specific volume, and when we want to locate state 3, we will need at least one property using which state 3 will have to be found out. And we can use the energy, we will have to use the energy balance, which will require the enthalpies. So if I just look at state 1, I can find out what is the specific enthalpy and the specific volume at state 1. And if I just look at a constant enthalpy line which passes through state 1, you can see this has a value. This is 20, this will be 18, this is 16, 14, this will be 13 kilojoules per kilogram dry air. So that is the specific enthalpy over here, which is 13 kilojoules per kilogram dry air, and the specific volume will also have to be worked out. This is 0.80, and this over here will be 0.79. So we are just below 0.79, approximately 0.789 meter cube per kilogram dry air is the specific volume. This is 0.78, you can see over here, and the one that we are interested in is the line over here, so it will be around 0.789. Similarly, at state 2, we will find out the specific enthalpy. And draw a constant specific enthalpy line, and you can see the specific enthalpy is 51 kilojoules per kilogram dry air. The specific volume, this will be a constant specific volume line which has a value of 0.86, and this is we actually are, so this is 0.85, this line over here, which I'll again show to you. The one that I'm drawing right now has a specific volume of 0.85, and this one over here is 0.86. So we are around the 0.858 meter cube per kilogram dry air mark. So that will be the specific volume at state 2. And let's just confirm those values. You can see I have those values over here, and using the specific volume and the volume flow rate, we can calculate the mass flow rate of dry air. Remember, the volume flow rate is in meter cube per second, which will be divided by the specific volume, which is meter cube per kilogram dry air. So the resultant units will be kilogram dry air per second. So the mass flow rates for stream 1 and stream 2 are obtained. The next thing is to perform a mass balance to give you the mass flow rate in stream 3. Then using the energy balance, we can find out the enthalpy at state 3, which is around 41.2 kilojoule per kilogram dry air. As I told you, we will need at least one property of state 3 using which we can locate state 3 on the straight line joining states 1 and 2, and that property is the specific enthalpy that we have just calculated. So I will use this value on the psychrometric chart to locate state 3. So I have to first find out a specific enthalpy value of around 41.2 kilojoule per kilogram. This is 40, this is 41, so 41.2 is just around over here. And all I have to do is to draw a straight line before that. I will draw a straight line connecting states 1 and 2. And on this straight line, I will then locate state 3 using the specific enthalpy. And you can see I have now located state 3 on the psychrometric chart. And we were asked to find out the dry bulb and wet bulb temperatures at this state point. So if I want to calculate the dry bulb temperature over here, I will have to drop a straight line from over here. So it's approximately 19.5 or 19.6 degree C. And to find out the wet bulb temperature, we have to draw a constant wet bulb temperature line which passes through this state point. And if I take a constant wet bulb temperature line, which is passing through this state point, it is around 14.6, 14.7 degree C. Okay. You can read it off from this scale over here. If I just draw a single line over here, so the 41.9 line will be passing through over here. This will be the state point. At 3 over here, the dry bulb temperature will be around 19.5 degrees C, and the wet bulb temperature, if you look at it, this is 15 degrees C over here. This line I will draw 15 degrees C wet bulb temperature line first. This is a 15 degree C wet bulb temperature line. Then I will also identify the 14 degree C wet bulb temperature line. So this is 15 degree C, this is 14 degree C over here, and we are roughly midway between the two lines. So the wet bulb temperature is around 14.6 degree or 14.5 degrees C. And I will go back to the problem that we were solving, and you can see the values that I have written down over here. Of course, as I told you earlier, these values are obtained by using the actual psychrometric chart and using scales to read off the values. Right now I am just visually giving you the values, which you can see are quite close to the values that I have worked out separately. The next process is one of sensible heating or sensible cooling, which is obtained by passing air over a heating or cooling coil. And during this process, the humidity ratio of the air remains unchanged. That means there is no addition or removal of the moisture from the air stream. As a result, the process line will be a horizontal line sketched on the psychrometric chart. As you can see, if you are starting with state 1 and the air is being sensibly heated, then its dry temperature will increase to that shown at state 2. If you are going through a sensible cooling process, the direction will be the other way around. You will be moving from a higher dry bulb temperature to a lower dry bulb temperature, but the humidity ratio will remain unchanged. In air conditioning, sensible heating is typically done by passing air over either electrical strip heaters or over a bank of tubes, which is called a heating coil, inside which some heating medium is circulating. For example, you can have steam passing through those tubes, and when the air passes over the tube bank, it is sensibly heated. On the other hand, if you are trying to cool the air sensibly, then you will have a cooling medium passing through a tube bank, which will be now a cooling coil, and when the air passes over the cooling coil, its dry bulb temperature will decrease. One particular thing or condition that applies to sensible cooling is that the coil surface temperature must remain above the dew point temperature of the air. And the reason is that if the coil surface temperature is at or below the dew point temperature, when the air comes in contact with the coil, that will lead to condensation, that is removal of moisture, and so the constant humidity ratio condition will not be maintained, which we want to be there when we are talking about sensible cooling. So that is an essential requirement, that the cooling coil surface temperature should remain above the dew point temperature of air.